So the next thing that I have to do is to implement the Barnset algorithm. But I'm not really sure if I'm going to implement or not, because I might try to implement a variation of it. Now I have a better understanding of how it works. So I'm going to see, I'm going to study the data structure that Godot has. I'm going to explain first how I think it works now. And then probably going to study the implementation that I did. I copied the implementation I did on the front end. I copied from some source code that I forgot where I got it from. And then I made some slight modifications so that it worked on the case that I had there, which is basically the parts that I changed were mainly for the inputs and outputs, like the connection that the algorithm had with the whole. So I took from somewhere else that it was open source, and then I changed enough so that it worked on the website that I had there. But I didn't take time to understand how it worked. I spent enough time on it so that I got it to work, because I had other stuff to solve, obviously. But now I studied more on how it works, and I'm going to see if I can implement something from first principles, because it might be just better than trying to implement Barnset. So, because I don't have it's not a requirement for me to implement Barnset. So I just wanna maybe test stuff out and see what is the easiest thing that I can do that is gonna give me like a feel of physics, like some resemblance of reality, let's say, of a graph network on display. And I think that is probably going to be more important to implement layouts. And there's a bunch of different stuffs that I have to. I'm basically going to look at it as an experiment. So I'm just going to try a bunch of experiments to see what kinds of visualization are better. I'm going to spend 2 hours here today. And obviously it's going to take some time, I think, to study everything and understand. So basically, this website here is the best explanation that I found. But it's very simple, actually. It's simpler than I thought. It basically works with space partitioning. So the first principle, I think, is space partitioning, which makes it faster than to just iterate over all the nodes. Because what Barnset does is just approximates the center of mass of nodes and calculate the forces based on the distance. So the further away a node is, as far as I understand right now, from the other node, instead of calculating all the other nodes that are on the same space as that node, it's just going to get the center of mass of that node, and it's going to simplify that way, and it's going to apply the force from the center of mass. And the center of mass is just a weighted average of the nodes on the space. So basically, the fundamental is partitioning, which means that you're gonna break down space into a tree data structure, because it becomes because it allows you to do these searches on the tree. That makes it faster to do physical calculations, because then you can simplify depending on the recursive steps on the tree, the depth of the tree. Amount of nodes are going to be like the way you divide the space. So it's 4 on the quad tree on 2 dimensions, because it's a square, so it has 4 different points. And on 3 dimensions, a octree, because it's a cube that you're going to divide the space from. And the way that it works is that the leaf nodes, the like outer nodes of the tree, the ones at the bottom, let's say, of the tree, are the ones that are bodies, and all the other nodes that connect all of them are encode the space, pretty much. So and then basically in order to insert the nodes, you're gonna do it based on the space, which is gonna take into consideration the position. I have color here, like this other color. They are gonna hold the center of mass of the nodes that are children of them. So an NE, for example, center of mass of D and B and C. And yeah, it's basically based on that it works. So there's this calculation. This part I don't understand very well, which is a part that I don't like that much. But the threshold is theta, which is an arbitrary number that you put there. I think it goes from 0 and 1 or something like that. And it's dividing as, I wrote down here, as this part is the one that I didn't understand very well. S is the width of the region represented by the internal node. So I don't know exactly what that means. If it means that it's just the level of the tree, or it can't be the distance, because D is already the distance between the body and the node center of mass. So yeah, I don't understand what S is very well. But then basically based on this, I realized that I was also seeing ChatGPT as well and searching the source code, because I realized that why not search for if Godot already has an implementation of an octree that I can use. Because the first step is to implement an octree, then you put all the nodes on the octree. Then after you put all the nodes, then you calculate the forces. That's basically how it works. And I was looking for Godot's implementation, if Godot has an implementation of octree. And then I found that they have this other implementation, which is bounded volume bounding volume hierarchy or something like that. There's a description on the other, and there's all these classes here that obviously I don't know them very well, but it's basically the same idea. It's just gonna divide the space using a tree data structure to make operations on the space faster, depending on what you wanna do. So, and the other thing that I learned is that this other thing that I've seen somewhere in other parts of the code is called AAB. Is an acronym for Axis Aligned Bounding Box, which I assume is just basically a data structure that is going to create a box in 3D. And I found somewhere that it looks like you can compare the boxes without having a bunch of values. The only values you need are the minimum and the maximum of the box to calculate the boundaries or something like that. But I think that these data structures here, they are used for calculating collisions, so they're different. But I asked ChatGPT and Perplexity, and they both said that you can implement Barnsat using BVH, and that's the reason why I'm thinking about the dynamic bounding volume hierarchy. It is here. So there is a dynamic BVH, which is BVH stands for bounding volume hierarchy. So basically, this learning how Barnstat actually works made me realize that maybe I don't even need to implement Barnstat. It might be more interesting to implement something else, because the main idea, the fundamental principle, is to define space using a tree data structure, which allows you to optimize in different ways calculations that you want to So obviously, I'm not really sure if I'm gonna be able, or not be able, but if it's gonna be a good idea to implement, because since this BVH is more usually probably designed for collisions, it might not be very good, or it might take unnecessary amounts of work to implement branch slots using this. But it feels like it's something that's probably gonna be. Obviously, I think it is a fundamental pattern. It makes a lot of sense to divide the space. So I think that's the thing that I have to learn more, how understand how it usually works. The A and B thing is probably the boundaries of the boxes. It's kind of hard to understand how it works. And also the logic for deciding how to divide the space. I think those are the two main doubts that I have now. If this is like overly complicated, then I might try to just implement something from scratch, because then it's gonna be a lot simpler, I think. But either way, in order to be able to do that, I think it's probably a good idea to study this anyway. Or I can look online or ask ChatGPT, see different implementations. I found some implementations of octaries, I think. But the problem is with other implementations, I think it might be harder because you have to remove everything that is related to the framework, whatever framework the implementation is gonna use, which might take like unnecessary amounts of time. So like the key, I think, is to try to study all of them to understand the fundamental principles and then try to apply from fundamental principles. Just thinking about. So I'm gonna think about, I have to think about questions, good questions to ask as I'm reading this stuff to try to clarify what is the direction that is gonna be the best to create this. I think this is the hardest part in the beginning because it's very confusing since I don't know, and there isn't anything under the, as far as I can tell, maybe I'm searching the wrong way, but I couldn't find anything on the documentation, and I think the explanations on ChatGPT and on Perplexity are outdated because of the time. So I think both Perplexity and ChatGPT gave me a link to a discussion that they had, this discussion here, because they used to have an octree and then they changed to this stuff. So there isn't anything that explains what is the purpose of this and how it works. I think it's basically used on the physics server, and it's going to be used for calculating collisions. But I don't, obviously I have no idea of how it's used. So the most annoying part is understanding the context behind everything, and then thinking about how to either simplify or do something else. Obviously I want to avoid doing a bunch of unnecessary things. Because this is something I find very often, but I think it's just the nature of programming that, like, usually if you find code, it's gonna be way more, it's like gonna be overly complicated for what you want to do, because it's not exactly what you want to do. Like the code was developed for something else. So the whole process that takes a lot of time, and a lot of times it feels unnecessary, but obviously looking backwards is easier, is that like if you started from scratch, you wouldn't need to do as much of the work, because for your particular case, it's not, it didn't have to be that way. Like there are other ways to do it that are a lot simpler. But then obviously the challenge is figuring out how to simplify or how to change things so that you can do it, or how to learn from the thing and then implement on your own. just gonna probably just read this because here there isn't anything that like allows me to understand. It's just the operations that's obviously the functions to add stuff, but I don't understand anything very well just by reading this code. So I think that probably the main thing to do first is just try to look for the class on, like, see if I can find where they implement this class on other parts of the code, and then look from that point. One of the most confusing parts is this thing about the minimum. These are, I'm gonna study a lot more of this, obviously, but I think the main keyword, the main direction to go is spatial acceleration structures. That's the main keyword, probably, to study these things. I think that the main question that I have, one of the main questions that I have is how do they simplify comparison between boxes by using only minimum and maximum values of position. And obviously, yeah, I wrote down this. There are the steps there. Maybe I should show on the article. Single body. So like how to add the node. It's another thing that is kind of confusing. Because like this is the problem, is that the article doesn't explain, from my point of view, it doesn't explain very well. I couldn't understand how to do the conditions here. This is basically pseudocode that they are telling on how to implement. So the idea that I had is just to read this article that I have there on the content. But now I'm not really sure, because I also think it's interesting to, because I want to see if I can extract the fundamental principles. Maybe I should try to implement it from scratch. Like the downside of implementing from scratch is that you never know if it's going to be a very good implementation, even if it works. That's kind of the challenge always, I think, as well with programming. It's, even if I'm able to implement, I'm not gonna be able to know. And I guess this is the whole thing about like getting other people code is better, because usually they spend a bunch of time thinking about it and they made the mistakes, so you can learn from them. But then it's also annoying because it's gonna be overly complicated for the stuff that you wanna do. I'm not really sure. So these are basically the steps for implementing the code. Node X does not contain a body, put the new body B here. If node X is an internal node, update the center of mass and total mass of X, recursively insert the body B in the appropriate quadrant. Node X is an external node, say containing a body named C. Then there are two bodies B and C in the same region. Subdivide the region further by creating 4 children. So that's basically what it's saying, is that like when you want to add the node, you're gonna traverse the tree and then check what kind of type the node is, and then based on the values of the distance of the current node that you're trying to add and the values of the current node, you are gonna see if this node that you're trying to add is gonna be a child, I think, or it's gonna be, or yeah, but if it's going to be a child, then it's in the same position, I think, as the current internal node. And if it isn't, then it means that it should be a sibling. The hard part is figuring out, it's understanding when you should subdivide the space and how you should subdivide the space. And then how to pick the main box, that's the thing. So I think that the main box you have to pick based on maybe the camera visualization. Yeah, but this is kind of the problem, because if you pick the main box based on the graph, then it defeats the purpose, I think, because then you're gonna have to traverse all the nodes to get the position of all of them, which doesn't make any sense. Because then you're just doing the work to avoid doing the work, which doesn't make sense. And then if you pick like just an arbitrary value, then there's a chance you're not going to calculate. Because if a node is outside of the box that you choose, then it's just going to be ignored. So or it's gonna be the wrong calculation, I think. Oh, but maybe as you insert a node, you create the boundary. You create the, yeah, but then, like, this is kind of the part that is confusing, I think. That doesn't explain very well in this article. Because maybe, I'm imagining, like, because these 4 values here in 2 dimensions are going to be the values of the edges I'm thinking about, of this quads here, this square. So, like, obviously, you're going to have to pick vector 3 positions for each one. So if you, like, depending on which node you add first, if you do it based on that, then it might be a different value of these vectors. And then later on, let's say there's a node that is outside of those boundaries, then, like, you would have to change the whole tree again, which doesn't make a lot of sense to me. Because then, like, every time that you update one of these values that is the high level of the tree, let's say, all the children of that node will have to be recomputed because the boundaries change. So the whole space division changes again. And this is a part that I'm not really sure if I understand. Node X is an external node, say, containing a body named C. Then there are 2 bodies B and C. Subdivide the region further by creating 4 children. Then recursively insert both B and C into the appropriate quadrants. This B and C may still end up in the same quadrants. There may be... The other thing that I was thinking about, but I'm not really sure if that makes any sense. Like, yeah, but it probably doesn't make a lot of sense because, like, you're dividing the space into cubes, and there might be some ways to divide. Because basically, I think the fundamental principle is that the structure of the tree is going to be a reflection of the geometry used to divide the space. So Octree obviously has 8 children because you're picking the vertices of the geometry to do the calculation. So I think that the structure of the tree is a reflection of how you want to sacrifice accuracy to optimize speed, depending on parameters you put, based on the way that you want to subdivide the space. So it made me think about why do people pick cubes, but I think it makes sense because that's the thing, because of the stuff from physics, it makes you kind of think because of the whole thing about there are no straight lines on the universe. So, like, usually you pick cubes because it's an approximation, but maybe for speed that's better. So you're sacrificing accuracy for speed, and that's just the tendency of computation because of abstraction. So mathematics is a reduction of reality because it's, like, faster, but then you sacrifice accuracy. So imagine that there's going to be a function that is a gradient that is going to fluctuate, which is going to be a reflection of the size of the tree, or of the structure of the tree. So I guess this is the main fundamental question to clarify. Is, like, how to determine the ranges. But I still have no idea how to go about doing any of this, or... It's hard to think about, like, what question to ask. in order to clarify this stuff here. So maybe you should start by studying the AAMB, access aligned bounding box class, to understand how and what stuff you can do with it. I'm trying to think about what are good questions to clarify this stuff here. I don't remember. I should have saved the place where I've heard about this. But I think that's on the, maybe there's a comment here somewhere. Probably on the dynamic PVH 3. Maybe it was on the code that I found this. It might be a better idea to just try to implement this stuff from scratch, because I think it might be a lot simpler, and then it's going to allow me to understand more how it works in case you want to change stuff later. So I'm thinking about if I can clarify this. Probably this is the best way to go about doing this. Is like clarify the fundamental principles, then figure out what questions to ask about the fundamental principles. And then after clarifying everything, then look for the classes. If there are classes here, if there isn't, then I just implement from scratch, I think. But probably the AABB class I'm gonna have to use. Not have to, but it's gonna be a lot easier, I think, if I use it. Because it's already designed to work with other Godot functionality. Is a struct, not a class. I think it was this one that's obviously this one's gonna have functionality to check. But it's probably on the dynamic PVH that I found some comment or something explaining the functionality to compare things. I'm gonna look a little bit more, and then I'm gonna spend some time just thinking about questions to ask based on the stuff from fundamental principles. Because I think I might, if The main problem is that I'm not going to be able to know for sure if I'm implementing in the best way possible. But I think it probably doesn't matter that much. You can improve. Because I'm not really sure. I'm contemplating which way it is better to go about it. Either trying to use the data structure that they have here, which are probably already more optimized for like kinds of calculations that are similar to this, or if I should try to implement it completely from scratch. Because I do think that it doesn't sound very hard. Because it's basically just building the tree. So like I can build function by function. I think one of the main questions that I have is just the boundary of the first boundary. You put the space, and the other boundaries are gonna be. Yeah, so I think it's a heuristic. That's the problem. So I think this is kind of the paradox, because the way you shape the tree is going to be based on the heuristic you choose to subdivide the space depending on the position of nodes that you're putting on the tree. So the question is, how do you determine? Because obviously, if you think, and I think that's where it's different the way that dynamic BVH works, because I think BVH is more for when you have a mesh and you want to calculate the boundaries of the mesh, because it's done for collision. So I assume that's the purpose. So I think on BVH you have a connected geometry, and you want to figure out the boundaries of that geometry in relation to the external environment. But for the thing that I want is a graph, so it's like a disconnected geometry. So the issue is, because the connection between the nodes that are going to make up the geometry, that is a reflection of the tree, is going to determine the structure of the tree. Like what is the best way? Because of the stuff that I said there before, where like depending on what heuristics you choose to subdivide the space, depending on what is the position of the node you're inserting into the tree, is gonna become faster or slower to rebalance the tree on situations where you have nodes outside of the edge of the boundary. So I think like just based on Front principles, I can see a way to kind of implement. So let's say, for example, we just speak. So just like they have here on the beginning. On here, I'm not really sure if maybe it's this class. Yeah, this is supposed to be the bounding box, right? The bounding box class. So they have the function there for initializing, which receives, maybe it's not this one. Is this? Receives the position and the size. No, I don't remember. I would use I think this is just a class to manage different trees. I don't understand why they do this, but maybe it's a reflection on geometry whenever you have different geometries and you want to connect them or whatever. Because the tree is just basically dividing the space. So this is, I think, the fundamental relationship, is the connection between the space and the geometry. I think that's going to define the structure of the tree. That is the best. Because obviously you're always partitioning the space because you want to do something in relation to a geometry. So I think this might be the reason why they have this class here to create a bunch of different trees, because it's a reflection of the connection of different geometries, but I'm not really sure. But probably I would use this class here, I think. So let's say you initialize the class and you have the... if you only have one value, then it gets into this confusing thing about the minimum and maximum of the box. Because it's kind of hard to think about how to build the algorithm if you only have the minimum and maximum. But let's say you have the 8 vertices of the cube. I guess you can just get... You can do geometry basically, but I'm going to have to think about the annoying details to calculate the positions based on only one point, I think. So like you basically build a cube based on some parameters from one position. So you initialize the class with one position and the size. Then based on the size, you build a square, and then you obviously use like some trigonometry, simple math to build the cube on 3 spaces. And then you're gonna have 8 nodes. Each node is gonna have its value of the position of the node, and those would be like the boundaries of the tree there. The first nodes. Then these nodes would hold the state, should determine that they are a position node, let's say, like part of the space partitioning node and not a body. And they would hold the mass and the position of the children as well. So it's just basically changing the states. Like you have 2 different types of nodes, or you can do the same node and just change the values of the member variables of each node. And then based on the heuristics you put, because this is the main problem, I think. Like the children, the collection of the children that builds up the geometry is going to determine the range of the cube, the space that is partitioning. So how does so like if a node falls into the range of the 8 vertices, 8 nodes, then it expands the tree. But then if it doesn't, if it falls outside, you would have to restructure the 8 base nodes. And I guess this is the most challenging part. Is thinking about how to restructure the tree based on the range of the space. And I guess this is the reason why it's kind of confusing, because one way to think about it is you have the geometry on space, and then from the geometry you do the space partitioning, and the other one is you pick an arbitrary range, and then from the range you calculate the nodes. And obviously I think that probably the best approach is going to be somewhere along the middle of these 2 extremes. One approach, I think, for example, would be but it doesn't make sense. I was gonna say like you put one limit at -infinity, for example, and the other one plus infinity, but then like how do you build a cube from that? Or put a very large number. And obviously the other way would be to just calculate but then it goes to the part that I talk about, that it defeats if you have to calculate the positions of everything on the geometry in order to be able to build a space. It doesn't make sense. So I guess this is the question that the article didn't explain very well, in my opinion. That is kind of hard to understand. Like how should we go about setting the first nodes so you determine the range of the tree? I'm trying to see. Maybe it wasn't. Yeah, so it was here. So those are implementations. And it's kind of weird that it has implementations here, but it also has the C++ file. So it looks like it initializes this bounding box with just the position. You can initialize with just the position and the size, or just an empty thing. So imagine that one of these functions that are going to be used to, or probably on all of them, they build the geometry from the first position. And then how does that work? The volume is just size multiplied, I think. Or just the 3 dimensions multiplied. So we got position, south position. Maybe, I'm pretty sure that A and B class they have on the documentation. A, BV class. Oh, the other thing that I was thinking about is studying the Godot Jolt physics engine, because people say it's better. So Godot Jolt is an extension for Godot that allows to implement the Jolt physics engine. Which seems that is better than the engine that Godot uses, so I might study that at some point. I have the documentation open, I think, for a sure. So this is the repository for the Godot Jounts. I already have the source code. The team variant type represents an axis line bound. It is defined by its position and size, which are vector 3. It is frequently used for overlap tasks. If itself is axis aligned, it can be combined with transform 3D to represent a rotated or skewed bounding box. Uses fluid points coordinates. The 2D counterpart to structure. I might read this again, because whatever. But probably not gonna have much stuff, I think. Maybe it does, because of the Godot classes, to understand the Godot classes better. It's probably better to just study the documentation, or the source code. So I'm just gonna ask ChatGPT. Because I want to, I'm mainly trying to understand when, because it's kind of weird on Godot as well, on the other ones, like it's not very intuitive to me to understand. Like, all the stuff related to math is kind of weird to me and not very intuitive to understand how it works. Because on the Transform 3D and I think basis is a part of Transform 3D. So a Transform 3D is a basis class and origin vector 3. So a basis is just a 3x3 matrix. And it seems that the way that they do most things is usually like you create different bases and then you compose bases based on each other. So it's kind of weird to explain. But I think a lot of the functions like the functionality is on the constructor of the class. It's not a method of the class, it's the constructor. And that's the part that is kind of weird to understand. Because for me, it makes more sense to have the functionality on the methods. So is probably the same line of thinking, but I'm not really sure. So I'm trying to understand what is the way that they usually use this. And also not only this class, but the dynamic VH class, because then the more obviously I clarify how they use the thing, it's going to become easier to understand like what is the point behind the methods. Hey, what's up? Godot is a game engine. A gaming engine is just basically a bunch of collection of tools that allows you to, it makes it easier to build games or applications. So it has a rendering system, a physics engine for calculations, then a thing for audio and multiplayer stuff that is related to networking, and I think other functionality as well. That's, I don't remember right now. So I guess I have to look into these functions here. Because if you only start with the, so I'm gonna look into this one, get longest access. So I want to understand how they, from the initial point, how they build. That's kind of weird. Also, just returning the, like the unit vector axis and comparing based on the size. So it's different than what I was imagining previously. Like the way that I was thinking about it is that you're gonna have the beginning point there, which is the position, and you're gonna have the size, and then they're gonna on the side of these functions they're gonna calculate the other vertices in some situations. Maybe they do that still. But maybe you don't need to do that because of the whole thing about comparing just based on two different points. Yeah, I want to see, maybe it was here that I found. Origin of the software, blah, blah, blah. It was this thing here. No, but it was somewhere else that I forgot. So you basically have the minimum and maximum and you compare the two. Yeah, so this function probably is checking to see, also the volume is already this thing. It's probably checking to see if one box is inside of the other, or yeah, pretty much. So I have to see the size. I think it's probably like I'm overcomplicating in my mind because it's very simple. You just do it to the nature of the box. It's always going to be the case that you're going to have a minimum edge and a maximum edge on both x and y, x, y, and z directions because they're like opposites of each other, and that defines the geometry of the cube. And the other ones are going to be just based on the value of the size, obviously, because you're calculating based on the distance from each point. So yeah, I think that's pretty much as simple as that, probably. So because it's always the case, you have the minimum and maximum vertices. You can check to see, just comparing those two vertices, to see if the boxes intersect with each other or if they are inside of each other. I think that's how it works. I'm gonna ask ChatGPT just this simple question. Why is it possible to compare? To compare. I'm just gonna see what it says. It's possible to compare two different bounding volumes because these values encapsulate all the geometric information necessary to describe the bounding blocks. Here's why these two vectors are sufficient. So I guess the other question is how to. So this is the kind of the thing. It's kind of hard to. Because if I think only if the information that they have there is probably not going to be. Maybe it is. But maybe if I use this class here, I'm going to have enough. So let me see what is the minimum. So this one has minimum and maximum. Let me see the constructor. It doesn't have a constructor. So I have to see if this is initialized anywhere. So like after, because if I need the minimum and maximum, then I'm not going to be able to use only the A and B. I still don't know which way is better to go about it. If I should build from scratch or if I should try to implement from using these classes that they have here. But if I have the minimum and maximum, then you can probably build all the other vertices from those things, having the size of the cube. So I think those are the two key things. Is the minimum and maximum vertices. They are going to define the geometry. And there's also the, like, how do you know for sure? So probably you build everything from one point, I think. So you just put the position and the size, and then you calculate everything else from that information. But then it's also tricky because, like, there's going to be different approaches to even that, because then but I think if you always go to the right, then it doesn't matter that much. So you start from the beginning points, and you assume that the beginning point is going to be the minimum point, which is going to be on the left bottom of the geometry. And then you build all the other vertices based on that point and the size you have. I think that's how usually you do it. But then the question would be, what defines the maximum? And obviously, I think it's going to be a comparison, but then there's probably different ways to do it. So the question is, what is the best way to figure out? I guess, like, if you're building from the points, then yeah, you can just think about it in your head. There's gonna be some triangle math probably. So like you build one square, and then you do triangle, the angles on the triangle you build, and there's gonna be something probably that people already have done to calculate this. So you can just decide based on whatever logic you use. Sure, like the last point you create is the maximum, which is the top right vertex, which I think is going to be the maximum. So if I do it from scratch, then I think it's going to be more annoying because I'm going to have to implement these things, but there's higher risk that it's not going to be the best. Why is the minimum? Yeah, so it looks like this is a binary tree. Maybe not, because this is 3, so yeah, it's not a binary tree, I think. Because each node is going to have 3 children, 0 index, I think. But maybe not, maybe it is a binary tree. Because they're checking here if it's a leaf based on the first one. So I guess it is a binary tree. Because each node has children, probably. But I'm not really sure. And these checks, you see, the internal nodes are the ones that, like I said, based on the article here. Internal is anything that is not a body. So the node becomes a body if it is on the region and it's not anything to subdivide anymore, I think. And that's why on this one, these two are bodies, but these ones are internal, I think. Even though they are at the edge of the tree. So this is how they define here. There's a null pointer. Is a leaf. If the children are null pointer is a leaf. And the internal is not a leaf. So I guess this is different than the one that they have on the article there. Because this one, you're gonna have leaves that are not internal, I think. Or maybe the body and the empty quadrants are the same. Are classified the same as external nodes. Yeah, I think that there probably is the case. It is the case. So external nodes are just the nodes that are on the edge of the tree. And the internal are the ones that are inside. And I think on the Barn set case, it's possible to have a body on an internal node, probably. Yeah, because that would mean that you would have the same, you would have a body as a child of the other one. It doesn't make sense. So I think on the Barn set tree, all the external nodes are either going to be empty quadrants or bodies, and the internal nodes are the regions of the space subdivision. I guess this is going to be probably the best function to see. Maybe not really. So maybe on the A and B, I have to find a function that they use to compare different nodes. I think, yeah, but it's just going to be the check between minimum and maximum. So I have to, on that function that they compare minimum and maximum, I can just look for places where they implement that to see how they do it. That's probably the best way to see. I think, yeah, probably this is used for raycasting as well. To see what objects are in front of each other. Oh, this one is interesting as well. Just see how they insert nodes on this tree. And it doesn't have a constructor. I think the most interesting, I think at least I think it doesn't have a constructor. So the most interesting are these inserts and the create node with volume. Split bounds. The bounds, yeah, let me look into all of this. So this is gonna be the box. Maybe I should start from the A and B again, like see how it works. So the minimum is the position. Yeah, so the maximum is just position plus size of the volume. This is kind of weird to me. So I guess the size is the... It is kind of weird because if you put a size that is on the negative parts, but the size doesn't make sense to be negative. There's always going to be growth to the right. So the size is just the diagonal, I think, of the box. So size is probably the diagonal. I'm gonna ask this shirt today. So if it is the difference, it's gonna be the vector of the diagonal, I think. So you're taking the points on the right top side of the box and subtracting by the left bottom, and then you get the vector which is on the diagonal, I think. Because the top right is always gonna be the maximum value of the cube, I think. But it depends on what kind of cube, obviously. But I think it's always gonna be like that. Hey, what's up? Hmm, interesting. I'm not trying to do anything actually. I'm just studying the implementation of different tree data structures from Godot because I was thinking about trying to implement the barn set solver, which is an algorithm used to simulate gravitational forces. So, which is what I am thinking about doing, but now I'm thinking about it might be interesting to try different variations of it. And I'm studying the class that Godot already has so that I can see whether or not I should use their classes or I should create everything from scratch. Should try to implement the barn set algorithm. Yeah, so it is what I was saying. But it can be the case. Yeah, I'm gonna ask that as well. Because if it is always one, then it means that the box. But if the name is axis aligned, so if it is axis aligned, then it should mean that it should be a straight thing. But then it also means because the z position, maybe actually is gonna be the top. It's gonna be the maximum is gonna be on the front of the cube, I think. But that wouldn't make a lot of sense because the z is negative going inside of the seam. So if the maximum was the corner behind the cube, then it wouldn't make sense because the z is negative. So yeah, I guess it's never the case where you have true minimum and maximum because one of the coordinates is always going to be smaller. Otherwise, it would be just a two-dimensional thing. But it's kind of because if the maximum is not the corner behind the cube, then it's kind of confusing to me how is it possible that you can see whether or not a box is instead of the other one if they just the minimum and maximum because they are both on the front of the cube. So it doesn't make a lot of sense. A back upper. So I do think that the way that I'm thinking is correct, but I'm not really sure how is it possible that the maximum is going to be higher because it has to be negative on the z axis, I think. So it makes sense that it's positive on is the highest value on the x and y, but it is not necessarily, it has to be smaller than the other ones on the z. Otherwise it wouldn't be a cube. Depends on how you look at it. Yeah. Someone's saying that the work is hard. Yeah, that's what I was thinking. So always has one by definition. So it's just the other way around. So the beginning point is on the back of the cube, and the highest value is on the front, I think. I don't think that this is the case. I think on Godot, when you increase Z, you go outside, you go further away. I think that Z is pointing towards the viewer, and negative Z is pointing inside of the scene, if I remember correctly. So it's starting to become more clear on my mind how it works. Yeah, but it's still, I think it has to be different. So the question I have is if, I think that those are the two, in order to decide whether or not I should use this dynamic BVH or if I should build it from scratch, I have to clarify why this is used. It's probably for collision or raycasting, both collision and raycasting, but like, what does that mean when it comes to the structure? So, because I think that to implement barn sets, I'm gonna need the 4 different or the 8 different vertices that make up the box. But obviously I can just change the classes that I have here to implement. But the thing that is kind of making me think that I should probably try to do it with this one is that they moved from Octree to this one because this one seems to be better. So if I could but then if I use this one, I have to change the way that I'm thinking about the barn sets implementation from the article there. So I think the main thing to understand is how do they use the minimum and maximum to subdivide the space, and in what context do they use this? That's the main direction, I think. So I should look for a place on the code where they use this one, but I have to decide first which one to use. So if I'm gonna so I'm just gonna ask GPT again, what is the difference between dynamic BVH and the tree BVH? Special optimized version of axis aligned by bounding box. So I'm gonna put in order of hierarchy of what I want to study there. So I'm gonna ask GPT what is the difference between this class because I want to pick one of them and then spend a bunch of time just focusing on that class. It's probably going to be dynamic BVH, I think. Yeah, but this is a problem. I'm not really sure if GPT is going to have any good response because I think that these classes are relatively new, so not really sure if ChatGPT has stuff. Or if I should trust that what it's saying here because it might be hallucinating stuff. Static BVH is primarily for spatial partition and efficient collision detection. Static structure changes during runtime. Yeah, so it's probably going to be dynamic BVH. Yeah. So I'm gonna focus on, So I'm gonna spend some time on this one and then focus on the other one. But it doesn't look that it is that hard to. So I'm gonna spend all of time studying the dynamic PVH, and I think that either I'm gonna build it on my own from scratch or use the dynamic PVH. But I think it's probably better to study dynamic PVH first. So if I'm gonna study dynamic PVH, I have to understand. I think the key thing to understand is how do they determine. So is the insertion of nodes. I'm gonna write down here. So the minimum and maximum thing I already understand now. It's just minimum is the position you initialize the thing with. Maximum is the minimum position plus size, and that's gonna create the. We're gonna get the two different vertices that make up the diagonal of the box. I think it might be different with the other one because of rotation, like ChatGPT said there. But for the A and B, A and BB is pretty much that because it acts as a line. So based on the minimum and maximum, you can just simplify the comparison to see if something is inside or outside of the box, or if it intersects with the box. So based on the minimum and maximum, I also have to understand. So I have to understand how they. Add nodes, and I have to look for a context. I think those are the two main things to understand. So once I understand this, then I'm gonna be able to think about whether or not I have to change or how like either way, like if I have to change the dynamic BVH so that I'm able to implement barn set with it, or if I change the barn set thing that I was gonna do and just do it with this dynamic BVH. So I'm gonna close this one. Now let me. So if it turns out that I can't study this right away, then I will study the other ones. I think it's probably better to just study that one, forget about these other ones. And this one I want, because it says that it's optimized version of the other one. Minimum means with a negative value in order to test them with SIMD. So the size on this one is minus negative max, minus the minimum. And so points depends on this. It's gonna be vector 3 probably. And bounds is A and B. I'm gonna ask ChatGPT again. So I don't understand why is this. And so just the opposite value of the maximum. So for each axis, it's going to update the value is merging with another A and B based on the minimum. I don't understand why this is the so optimize. It's not that hard to understand the functions with center. So center is just half the size plus the minimum point. Yeah, because obviously, like I said, the maximum is just the diagonal of the box. So the center, obviously the center is going to be the midpoint to the max. Yeah. So it's getting the two vectors of the diagonal of both and subtracting them. And then for each axis it adds to the absolute. It's just gonna add the three different values of the vector that it gets here. Yeah, minimum. A minimum minus negative max vector of the diagonal of one box. So it is the diagonal of one minus the diagonal of the other one. And this should give you the distance between them, I think. Or the vector that represents the distance. I'm not going to spend a bunch of time looking into or thinking about the intersection there. Because I'm trying to think more about how I'm going to potentially use this. Because I don't think I'm going to have to... Intersection between planes is probably more related to ray tracing. But I think for my thing there, probably... not, maybe it is necessary, but... Based on the way that I'm thinking now, it's probably not going to be that relevant, I think. Because it's more about, I think the most relevant thing is understanding how to add the nodes. How to grow the tree based on the space. I think that's the main thing. Because then, I think after this part, which, this part is probably the hardest one to understand. Because after this, then I think it's very simple because you can do the calculation of the forces based on the state of each node that you put there. So in case of the barn set would be just getting the weighted average of the points in case the distance is on the threshold there, on the theta threshold. You get the approximation of the center of mass and the distance, and then you calculate the velocity based on that, which is just the state of the class, I think. So let me move on to the, because I'm not gonna be able to understand very well what is the point of like why is the other one an optimized version of this. So this one is probably the one where they calculate the sizes, maybe. So it's just increasing the size basically for each position. So it's just like, it's very similar to when I was trying to render the quad for rendering text. It's basically the same stuff. You just increase by the size each vertex, then obviously you build a quad based on that. But I was thinking that for the other one, it might be necessary to have angles. But yeah, maybe like it doesn't make sense because the box is aligned with the axis. Because I was thinking about a box that would have two squares that are not aligned with each other, but then obviously it's not this one. So in my mind, thinking about like a diagonal box. Obviously this makes it a lot easier. I'm not really sure if the other one is going to be like this. It's not that hard. So in the case, like if I wanted to implement, and I think in order to implement the barn sets, probably the easiest way would be to just use this class here and then change the class a little bit so that I can add another function here that gives me all the sizes. And each one would be a node of the tree, obviously. So it would be 8 vertices. And then based on that, like you start off with an arbitrary range for the minimum and maximum. So with the minimum and the size, which defines the maximum. Then based on that, for each node, I create a function that is going to take some heuristic. Actually, it doesn't matter because it's just going to compare based on whatever initial condition I put, if the node is on the range or not. And if it isn't, then you change the range. And if it is, you just put, depending on whenever the position of the node is. So for each, the function would compare the minimum and maximum, I think, for each position of the node. So get the positions of the node you want to put on the tree, then you compare with the minimum and maximum of the A and B. That defines the roots. And then you do, like, based on whatever the value is, you have to compare, I think, on the 8 nodes. And then based on that, you see where the, yeah, but this is another question, is how do you determine, I guess this is another part that is confusing. Like how do you determine which quadrant you're gonna put? Because I would only have the true, I would have the value of the box in the beginning, so. I mean, maybe this is the points that I'm not understanding here. Because this is the part that is not clear here, I think. Because like, how do you determine? Like if node X does not contain a body, put the new body B here. But if we're talking about this one, then how do you know which quadrant to put the body? That's the thing that is confusing. I guess this is a like thing that is kind of hard to clarify, because he says region by talking about the vertices of the thing, but then like what does it mean to for a node to be on the region? Because the node represents just the vertex of the square. I guess it's just based on proximity. Yeah, that's probably, I guess that's the only thing that makes sense. So, like, in which quadrant the node's always going to depend on the distance between the node and all of them, I think. So you get the shortest distance always. It's probably, so like if you're doing breadth first search, for example, so you're going horizontally on which one, actually would get the distance of all of them compared to the node that you want to add. And then the minimum one is the node, the node that you add the other one. And then you check to see whether or not it has other nodes as children. Then if it has, then you do this process that they talk about here. That's probably the only thing, but they don't explicitly say this here, so. Also, they're doing. Oh, so the quadrant is not the vertex, is the. It has more positions. Yeah, I was thinking about it the wrong way. So I was thinking about each node is gonna be a vertex that defines the geometry, but it's like it probably has a state of all the 4 points that define this space. So they all start on the center of the geometry, and then you subdivide based on the. Yeah, that makes more sense. And then the check is just based on the boundaries, obviously. So like each node would have the 4 different vertices, and then for each node, you would check whether or not the node is smaller or lower, like is within the geometry. Just doing the if conditions to check based on the position, the value, if it's inside or outside. Then obviously if it is, then you put on the node. Yeah, so that makes more sense. But it becomes very confusing to think about. I guess it's always the same, so it doesn't matter how many times you subdivide because it's always going to be the same logic. So like the state of the node is always the same, which is the heuristic you use to subdivide the space. So it would be the calculation that they are doing there on the function, on this function here, to get the coordinates, but in a different way. So like you would just get half, for example, instead of making plus the size, you make plus half the size, and then if you do that for all the vertices, you get the sub regions of the main space, and then for the other nodes would be just the same thing. Yeah, so it's not that hard actually to think about it. It's just annoying because of all the vertices you have to create on 3 dimensions. And there are other annoying things that it doesn't scale overall, I think. But obviously it doesn't matter that much because I'm not going to be able to visualize in 4 dimensions, but it's still interesting to think about, I think. So this might be the reason why this other data structure might be easier to do it. There might be another way to compare. I think that there are 2 keys. One is on the beginning when you initialize the tree. How do you define the size of the initial space? It has to be based on the geometry, but then how do you know if you don't have, what is the best way to know? Because if you do a space that doesn't fit the geometry, then you're going to have to resize the tree at some points. But obviously the safest way would probably to get a very big space, which is very likely that the geometry is inside, but then it's probably not optimal. But maybe it doesn't matter that much because the first... Yeah, but actually you would have to go through the entire geometry to make sure, I think, in order to decrease the size of the space. So I think that those are the main questions. Is the beginning size of the first geometry, and then how can you optimize the control flow inside of the loops should add the nodes based on the checks on the positions. And then the other optimization is going to be on the, like the differences in optimizations are going to be in the way that you decide to sacrifice accuracy for speed based on the tree traversal that you get the state to calculate and update the forces. So I'm gonna spend more time. I'm gonna actually study this one. So I'm gonna study this implementation that I have here to. But I'm thinking I'm gonna start with something different based on the stuff that Godot has there, or a variation of the stuff that Godot has. Yeah, I have to spend time thinking about like what is the best way to because it's probably the case. It might be the case actually. I'm not sure if it is likely or not that the stuff that they have on the A and B class is not enough to implement the solver. And then either I can implement like a class or a struct that inherits from the one, or create a completely new one with the functionality. Yeah, so I have to spend time like thinking about which way, but probably it's better to spend more time studying the class that they have first to make sure that. I think the main one that you focus on is the dynamic BVH, and then try to find how do they use the class to clarify. But it's becoming a lot more clear on my mind how to do it. It's basically just the thing that was confusing me is just the state, because I was separating the nodes in a different way, but in my mind, but it makes a lot more sense to have like the state of each node. You keep track of the vertices that make up the geometry that you're going to use to subdivide the space. But you can reduce that based on the size. So for each one, you would do some annoying calculation to just get the center of the thing. So yeah, you get the minimum and the maximum, and you get the center. From the center, you subdivide on the different parts based on the dimensions of the geometry you have. Then each node is going to have that state, the nodes that are regions. And then you have another type of node, which is just the body. Or you have the same node and you have a flag variable to determine if it's a body or a region. And then to add nodes, you just put a function to check the condition, see if the node's inside of the subspace. And if it is, you put on the quadrant, and then you check to see if there are already nodes there, and then you subdivide even more. And then after you create this function to add all the nodes, the other step is just going to be traversing the nodes and then putting an arbitrary depth, recursion depth you want. That is going to determine the distance of the nodes, like the threshold for the relationship between the center of mass, the distance between one node and the other node's center of mass. And then based on that, you update the forces. But I do remember that there are other stuff here. So yeah, this is basically, so there's 3 different solvers because I did this based on VGS. But the other solvers are kind of simple, I think, to do it. So the Barn set's the most complicated one, which is the one that I got from the other implementation. So this creates a tree based on the options. If I remember, the options are going to be a dictionary that has the default values there that I have. But this is one of the things that I wanted to remember is how are the options, the values on the options used. But I guess they're using other parts as well of the solvers. So I think on the Barn set it's probably only data that is used. And then there are the other values that are options that have to do with string length. The central gravity, it's probably better to write this down as well. So I remember. I'm only gonna write on the Barn set actually, because I'm doing the I'm gonna have to change the barn set parameter struct that I created based on this thing here for the GUI elements. Because if I change the solver, then obviously I'm gonna have to change the options. So I wanna see exactly which options are used from the for the barn set specifically. I know that uses data. Avoid overlap. That's probably, so only these ones. So first here, it creates the octree. I didn't like this implementation that much, to be honest, but it's the only one that I found that it worked and it was relatively easy to implement with this other stuff that I had. So that's the reason why I use it. So it creates this other thing here from the other file, which is a stack. It's basically a stack. And then it has these functions. So it has this function that it uses there. So this would be like a class and implemented in this weird way. So I initialize everything with all the values equal to null. So these are the 8 quadrants that it's going to use. Just determine where the node is at. Body, the max. I believe that I put this equal to 1 on the other thing. And obviously the mass is going to be used to calculate the force. I guess this is the positions. Let's say left, right, top, bottom, front, back. Yeah, I don't understand this very well. Bounding box coordinates. So this would be the AABB thing. And the other one are the quadrants that subdivide. It's kind of weird because like I would use the AA and BB as well for this stuff. But I guess each one of these would be its own AA and BB. Or I can do it based on one. So this is another difference in approach. So I can use one initial binding box, which is the way that I was thinking about. It's the first initial space, then you derive the quadrants based on the positions of the first bounding box. So the minimum, the maximum, the center. Then you get all the other positions, which are vector trees for the other quadrants. Or to build the quadrants. No, but I guess it makes more sense for each quadrant to be its own A and B, and for the main thing to be an A and B as well. Because the other ones are going to be A and B's, AABBs derived from the... So like what you have to do probably is to create a function that takes one A and BB and then creates other 8, which are the subdivision. The subdivision of the main one. So it creates the first node here. So I guess in the beginning is just creating the functions. So this would be like a class there, is just returning the functions. based on the stuff that it creates here. So it creates the roots and then returns the functions. Insert body here, notate. And this is probably a helper function, I think. No, this one. That this one's probably gonna use. Yeah, insert. So this one is probably so this is the function used to insert the node on the tree. The body is kind of confusing because the body is the node on the other circumstance. So like the body is the sphere of the graph that we're gonna put here. And this one obviously is the roots of the tree. So this is the thing that I was thinking. So here he decided to initialize the first parameters as like a very high number. So the first space creates a very high number, I think. And then from that point, you probably update the boundaries based on the nodes, but maybe not, because it doesn't matter. It's not like so it's comparing and then updating. So I think I already get it. So I'm probably not gonna. I don't think it's worth it to just transfer this stuff to the other one, because I don't like the way that this was structured, and I probably can like make one approach that is more intuitive to me if I do it from from scratch. The most annoying thing about this is just is like getting all the vectors correctly, making sure you get all the vectors correctly that are gonna make up the subspaces, and then also making sure that you got the checks correctly to see if position is inside or outside of one of the spaces. But so probably the way that I'm thinking about implementing is just by replacing the quadrants with A and B's. The first A and B I initialize with a very high boundary. Then from the high boundary, I get the subquadrants by dividing with the methods that they have there to find the center and the minimum. So I have to create a function or see if they already have there. But I'm going to spend time setting dynamic PVH first. Create a function that takes an AABV. So once you do that, then I think it's very easy. So it creates the nodes, then inserts the body, inserts the nodes. So this would be, these are all the nodes of the graph. Just putting all the nodes here. And then for each one, it calls update body force to calculate the force. 0. Yeah, so the bodies is inserting based on the boundaries. This part is kind of confusing because of the checks there, so it's kind of hard to visualize. With the x, it's checking to see if it's checking to see the small x, the smallest x. So it's 2 points, the maximum and minimum values. So this is kind of weird because it's going over all the nodes each time. I don't think this is very. Maybe there's a better way to do this. Because here is the thing that I was thinking about before, where it doesn't make a lot of sense that I was thinking about. It's like if you can loop over all the nodes to check the bounds of the entire geometry, of the minimum and maximum of the geometry, and then make the space you initialize the tree with based on the boundaries of the geometry. But then the reason why I thought that it might not be very good is because you would have to go over all the nodes before, and it would defeat the purpose of creating the thing. But I guess like the main reduction doesn't come from avoiding to loop over the entire geometry many times. It comes from approximating the values after you create the tree. But here, it does seem that there should be a way to make this better, I think. So here, for each node, I think. Oh no, it's only going once. That's basically what he's doing. He's getting the minimum and maximum based on the geometry you have. So you loop over all the nodes, and then you get the X, Y, and Z. Yeah, you get so you start with a very, very high and very small value, and then you get you update should be the position of the minimum and maximum based on the geometry you have. That's what he's doing. So I guess the max size and calculates this. I don't know why he calculates the minimum, but whatever. Calculates the minimum based on the max size. Oh, so it does this for every node, though. So that's probably not very good. So for each node is doing a O n to the power 2. So like a nested loop here. So for each node, it calculates the boundary. It's not very good, I think. I was thinking about it in a different way. Maybe it's because of this last part here. So I think, yeah. So this is just updating the minimum and maximum. So the left, right, so this can be replaced with true vector trees. That's basically what this is doing. So for each node, it's getting the new maximum and minimum for the bounding box. That's why it's doing this. And then for the body, it just assigns the node there. So root body contains the node that was inserted into that part of the tree. And then it's going over again here. So it's gonna call recursively until it gets to a point where it doesn't have I think. Yeah, I don't like the way that this was done. It's very confusing to me to understand. But I think I get it now, what it's doing. The part that I don't understand is because it's basically adding the nodes based on the range here of the space. But there isn't any check to see if two nodes are on the same quadrant. But I guess the check comes from from this already. Yeah, but I think it's a slightly different implementation than the article suggests doing there. Because here you're just going based on the position of each node, and then it's classifying the boundaries of the node, the box of the node, based on the values here. So, yeah. And then it builds the box based on the... Oh no, it might be because like for each time it's going over all of them again. I guess this is the part that's kind of confusing. I guess it's because of each time it's gonna pass the roots, which is the new node. Yeah, so each time that it calls recursively, it changes the boundaries because it's passing from this. This here. It's just gonna change. Oh no, this is the other function. That's fine. So I guess I was understanding it wrong because I thought it was recursive. So it runs that only once and then it calls this. So it finds the minimum and maximum of the geometry. I think that part was correct. But then it's gonna insert each one based on the minimum and maximum with the, like whatever node has the minimum and maximum. Or whatever check is there. See which one is the minimum and maximum. So this is the case that the article is talking about. So for each internal node, it's gonna store the average or the center of mass. Yeah, center of mass. Which is the weighted average of the position on the mass. So this is the part where it's subdividing again. So this function, I'm pretty sure, obviously, that this is going to be the one that's based on the if-else conditions here, is going to determine the type of node, and it's going to shape the tree based on what kind of node it is. So if it's internal nodes, it means it's a region, so it's just going to add this stuff, and then it's going to continue the function, I think. Because for each node, it's going to call this. So here, I think on this first part, it's just gonna, so it gets like an infinitely big, or like the maximum space that it gets based on the, so the maximum corner of the cube, the minimum. And then it goes over all the nodes you pass to make up the geometry. And these conditions here, I'm not really sure because I don't want to think about it, like the specifics. But I think they're gonna get the minimum and maximum for the geometry. Like these values here are gonna represent the minimum value that the geometry has. So it's like basically shrinking the initial space so that it fits the geometry based on whatever you pass, whatever bodies you pass, the positions of the bodies. Which is gonna be these values here. Yeah, so there's this calculation to update the minimum value here, which I don't understand very well why it does it like this, but yeah, it's gonna store on the first node the minimum and maximum for the entire geometry you pass there, which is basically the collection of positions you pass. And it stores on this, which is the bounding box of the roots. Then it makes the body of the roots should be equal to the current node. No, it is the last node, I think. So I equals to max, which is the body, which is the length of everything, the length of the vector passed there, of the array. And then here it makes it -1. It's kind of weird. I don't know why it does this here. And not I equals max -1 already in the beginning. Oh, because it is decreasing. Yeah, so it uses here to decrease, then it makes it. So the first node is going to be the last, I think. Does it change max? Probably not. Yeah. And then it's gonna call the function. So it's gonna call from the end of the vector to the beginning, and it's gonna call for each node and pass the roots. It's weird that here it only has this. So I'm not really sure what's going on here. I do remember like the first time that when I was making this happen there, I do remember that there was something weird here that I have to change it. I had to change a couple of times. It might have to do with the way that this works there, but I don't remember really well like what was the problem or what I changed. I guess the only difference is that this is gonna be the roots being initialized here. So the first node is not gonna be the one that has the minimum and maximum. It's not gonna be the bounding box of the entire geometry. It's just gonna be this first node here, I think. So I don't need to pass there. And then this function is going to have inside of this the control flow based on this data structure that they create there, which is a stack, to determine what kind of node it is, and then to update the values based on what kind of node it is. So I'm going to stop here. Probably the next time I'm going to continue to study this. I don't think I'm going to implement like this, but I'm just trying to clarify how it works. I already understand how it works, so I'm going to try to think from first principles. And the only thing that I'm not really sure is whether or not I should try to use dynamic BVH, class that Godot has there, and then think about how I can use it to implement the solver, or if I should go from the beginning on what I think the solver has to be, then add all the functions that are necessary to implement, and then after that see, or like change this class here, start from this class, then change this class. So either start from on my own from scratch or use this one. But now I have a pretty good idea of how it works. Oh, the main things that I still want to get from the other one is to check how these things are used there, because I'm gonna have to, or not gonna have to, but it might be useful to incorporate these values there, so that I don't have to change the GUI component that is going to be used to change the customization of the physics. So yeah, but basically, if I was going to implement from scratch, what I would do is just build an A and B from the beginning in the same way that they build here. So use like the maximum minimum values on C++ to build the first A and B, then create a function that splits the A and B into the subspaces, and which are going to be used to make up the child nodes, which are going to have the information on them of the vertices that make up the minimum and maximum of that subspace. Then create another function to check to see whether a node is, which subspace the node is located at. And then based on the article here, do the same thing that they tell you to do here, which is to check to see if there is another body there on the subspace, and if there is, then recursively call and subdivide the thing and add subspaces to as children of the current node, using the same function from the beginning. And then if there aren't, then turn that node, or I'm probably gonna set a flag variable, I think. So set a flag variable equal to true that indicates that the node is a body. And then that's basically the main thing. Then once you build the tree, all I have to do is just figure out how to traverse, and then update the values. That's probably how I'm gonna try to implement, but it's gonna take some time. So next time I'm probably gonna be either studying this or trying to implement this stuff. So see